Okay, now we're going to see something really cool that takes this idea of a limestone to a very different place in terms of what the graph ends up looking at. I promise you've never seen a graph like this before. It's got something pretty unique in it. It won't initially look like it's any different than the other ones that we've talked about. And we'll start with zeros, and we let 1 equal 1 plus 2 sine theta. So zeros are going to occur at, let's see, minus 1/2 equals sine theta. So that tells us that zeros should occur at 7 pi over 6 plus 2 pi k and 11 pi over 6 plus 2 pi k. And that's a little bit different, right? Because that's telling us that the zeros are happening at least 7 pi over 6 into the full rotation. That tells us, that's an immediate sign that this graph takes the full 2 pi to repeat, right? That I don't stop after pi and assume that I've seen all of the behavior, which will be important in a second. Keep that in mind, right? The zeros happen in the second half of the revolution. All right, and we want to know what the maximum point is. And the maximum point is going to occur when theta equals pi over 2. And at pi over 2, we're talking about 3 being the r value. So 3 pi over 2. And for symmetry, we should expect symmetry over the line theta equals pi over 2, because we're a function of sine. All right, so let's look at the initial values that I chose to consider. So 0, 1, and you know what, I'm going to double everything here. So I'm going to make this 1/2. I'm going to spread this out a little bit, just so we can get a better idea of what's happening. So we'll start here at 0, 1, pi over 6, 2. So we're going outward. Let's see. Pi over 4, 2.4. It's a similar, notice that these points tend to follow a similar pattern because we're just increasing. Pi over 2 up at, let's see, I think I made that too small. So I got to remember that this is 5/2 and this is 3. So 2.4 is just a little less than 5/2, and 2.7 is more as we get to 3. All right, so, and then I can go back down the other direction, and I know that it's reflective over this axis, so I can take my time to make sure that I get these points right on the other side. But I can feel confident in knowing that that's where these points belong ultimately, like that. Now we could assume that that's all the behavior and just connect it. Except we know, right, from the zeros that when I get to 7 pi over 6, right, that's a 0. And when I get back to 11 pi over 6, that's also a 0. And those aren't evenly spaced apart. So we got to figure out something else that's going on here. All right, so let's look at another set of points. So I'm going to add a few more points to our conversation. Let's just think about this set of points. So if at pi I'm at 1, here, if at pi I'm at 1, I'm at 7 pi over 6, I'm at 0. At 5 pi over 4, so at 5 pi over 4, I'm now at minus 0.4. So that means that I've got to switch over to the other side and get to right about here. And then at 4 pi over 3, I'm at minus 0.7. So again, I got to go up to minus 0.7. And then at 3 pi over 2, I'm at minus 1, which is here. Okay, so now we try to visualize, right? It's got to be reflective over the axis again. So I repeat, and I come back. And now the key is trying to figure out, okay, how do I draw this? Right? And let's just go in order of quadrant. So in the first quadrant, I go up, go over, I connect. And in the second quadrant, I do the same thing. Over, down, and connect. Now, let's go in order of points. So from pi to 7 pi over 6, I go under the axis to connect. And now when I get back to pi over 4, I'm going in the other direction. And up to 4 pi over 3, and over to 3 pi over 2. And that's got to be reflective. So I come back in the other direction and finish in the same manner I started. And look at that. Here we have a limestone, but because of the way it's structured, I end up with what we call an inner loop. Okay. So this limestone has an inner loop to it. It's got this inside piece. It's still reflective over theta equals pi over 2. It's still operates in the same way. We can still find the zeros, but it's got this inner loop based upon the way that it's defined. Pretty cool. Never seen a graph where we've been able to draw a loop inside the relation before. And just to give you a final piece of information, all limostones take the form, we talked about this in class, r equals a plus or minus b sine I, and r equals a plus or minus b cosine theta. I said b sine I, I meant b sine theta. And what you can see here, what I've laid out, is what happens based upon the relationship between a and b. And at the large, if you look back at the examples that we've done, if you take a look at the homework problems that you do tonight, okay, that as a and b change, the actual style of limestone that we're looking at changes with it. So the more, right, so we start over here, when a over b is greater than 2, we get almost a circle, but pretty convex. We saw a dimpled limestone. That was the first example that I put on video. In class, we did a cardioid. Right? So the one we did in class today, if you look back at the formula, was r equals 1 plus 1 sine theta. I believe the one that I did in the first example was r equals 3 plus 2 cosine theta. And the one I just did was r equals 1 plus 2 sine theta. Right? And look at how the ratio between a and b tells us more about the type of limestone that we end up with. I personally prefer the inner loop one. That's pretty cool. And again, we talked about how the circle really belongs within this family. It's just a different relationship between a and b. All right, so that should be enough information for you to graph those limestones tonight. Tomorrow we'll talk about flowers, petal graphs, and lemniscates, and all kinds of great stuff like that.